If I tell you that you have to wait for a certain amount of time t, but then in return I'll give you a certain reward p, then what is the chance that you will wait that amount of time t? Okay. Let's say this is a probability, a likelihood of that you will be waiting that long for this amount of reward. Now, what this would be would depends on the ratio of your price sensitivity versus delay tolerance, reflected in its dependence of these two arguments. So this is what we call a weighting function. Okay, with a little abuse of notation, we use w to denote the function as well. W as a function of t and p. Now this really should be a different function for different users and different applications. So if you've got 50 users, each got let's on average 100 applications, then you should have in full generality 4,000 or 5,000 different such weighting functions. But in general, for practical purposes, we'll group them into the similar classes. For example, we'll say that Alice and Bob belong to the same class, or email versus Facebook update belongs to the same class, and then we have fewer functions to estimate. Now, in order to talk more about this, we need to parameterize this function w. Now we know that w should be decreasing function in t, because longer you ask to wait, less chance you're willing to wait. It should also be at the same time increasing function in p, because the more pricing incentives you are given, the higher the chance that you will wait. Now, of course, there are many, uncountably infinite number of functions that are decreasing in t and increasing in p. But one typical and very simple parameterization is through the following form. We say that w as a function of t and p is simply p over t. Now, this is not the final answer. For one thing, t could be 0, so let's say t plus 1. Now, second, this is not really differentiating between your dependence on p versus t. So one possibility is to give the denominator power beta. So this is a function that is parameterized by beta. Beta is some positive real number that can parameterize different kinds of weighting functions. Now, in general, if you have a large beta, that means that you are not willing to wait a whole lot. If it's a small beta, then it means you are willing to wait a lot. For example, based on our own survey in the US, we found that beta is about 2.027 for YouTube streaming, and beta is instead 0.6355 for video download, for example, from iTunes. Okay, so this is a much smaller number, and therefore reflects a much more likely chance that you're going to wait. Okay, so different users, different apps, different demographics and countries, you can have different betas. Of course, you don't have to stick to this particular parameterization, but this is a fairly simple and quite useful one. And later in the homework, one of the problems asks you to run through an estimation of weighting functions. Now, suppose you have indeed run through an estimation of weighting functions. Now, the second step after that profiling step is the price optimization engine. Here, the price can be viewed as incentive or reduction in price or reward or credit to your monthly bill. Okay, so instead of say, now it's $10 a gigabyte, I'm going to give you a reduction down to $8 a gigabyte. If it's really needy of incentive for you to shift traffic into this, say, middle of the night, maybe $1 a gigabyte. Okay, now we're not going to presuppose a particular price. This should be discovered through an optimization problem. So what kind of optimization? As you may recall, we need an objective function, we need different constraints, and we need variables, and the rest will be constants if they are not variables. So what is our objective function here? For the carriers, there are two kinds of costs incurred now. One is the cost of exceeding capacity. That can translate into user churns or the capital expenditure you need to provide to increase capacity and over provision by the peak traffic. Okay. The other is the cost of reward, meaning that since you are not charging $10 but instead of $8 or $1, then you are giving away $2 or $9 in these two cases respectively, for example. So you got two kinds of costs and you want to balance their sum. And let's say you weighted a sum of them. A is the weighting parameter, some real positive number times the exceeding capacity cost plus the reward cost. And we'll see an example in detail soon. And then the constraint basically is to say that I need to maintain proper accounting of the traffic. For each given period, let's say I've got two periods here, okay? Period 1, period 2. If the traffic that goes away from period 1 into period 2 because of this incentive versus traffic that goes from period 2 back to period 1 because of incentives, you have to keep track of those traffic getting in and out of a given period. And the variables are indeed these price rewards. They are going to shape this part, and clearly they define this part of the objective, and they are constrained by your proper accounting rule. This is the optimization problem that we'll be dealing with. Now, before we show any examples, I want to highlight that there are also many system implementation issues involved here. It's not just a mathematical exercise, as in many of the upcoming lectures in this course. There are quite a few modules requiring different kind of coding capabilities. For example, we need a graphic user interface. The simplest one would be the best. And that means you have to interface with the iOS and Android and or Windows if you use Windows dongles for 3G and LTE. We also need traffic measurement and also mobility pattern analysis in order to run the profiling engine. We need the computational engines to run the price setting on a very dynamic basis. And we need a database, of course, which could be partially split into your phone or iPads and partially given to the ISPs. Okay, which part goes here, which part goes here, would in part depends on the privacy and security concerns. And you also need, of course, scheduling control software. Some of these may goes to the end user devices, okay, your phone and tablets. Some of that goes into gateways. For example, in your home, your cable provider may have a residential gateway together with a Wi-Fi. Okay, and some of that control software need to go into the back end, usually the control plane of the carriers. For example, we will see later in lecture 19 something called a PCRF in cellular 3G and 4G networks. Okay, you need software intelligence across all of these points in the network end to end. As you can see, this is a gigantic piece of implementation, involves many different elements and kinds of codes. I just want to highlight that this also says that basically you've got a network. Okay, this is your network. You've got also end user devices. The traditional network management software says the intelligence should all reside inside the network. But increasingly, you see these end user devices capable and essential part of the network management. And as you can see, some of that here, of these software elements actually need to be split architecturally and put onto the end user devices. Now, we run a trial of TDP in a project called Data.me here actually at Princeton with about 50 participants. And the same team is now going to launch commercial trials with 5 commercial carriers, including 3 of the largest in the US and India. But for this local Princeton small-scale trial that has been concluded already, what we observe is that we can see a 30% reduction in the peak average ratio. That is, you chop the peak, okay, relative to the average by 30%. Yet at the same time, you also see another almost magical thing, 107% increase in the average amount of usage over, say, a day or a week. The key word is that this is average. In other words, not only you chop the peak, dump it to the valley, but also raise the sea level. Use the metaphor of chopping, say, icebergs onto the ocean. Okay, the sea level also rise. The total usage or average over days usage rises, in fact, more than doubles. Why is that? Well, that's mostly because when people look at the design, okay, I skipped the graphic using today's interface design because it's really outside the scope of this course on networking. But one of the implementation gives you a color-coded tab on your home screen, and people look at that green button instead of red one, knowing that this is a very inexpensive, a cheap period to use the internet, and then they start to consume more. So it leads to both a reduction in cost and an increase in total usage that translates into better profit for the carriers. At the same time, it also translates into lower prices. Back to the motivating questions for this whole lecture. Lower prices per gigabyte for consumers like you and me. Plus it gives actually as a side benefits the power to choose between paying more for faster service and paying less, save money if you are capable of and willing to wait. So that is the win-win created by such a TDP trial. And I just want to illustrate one more time. This solid line is the traffic over a 24-hour period without TDP, and the dotted line is an example of what you get with TDP. As you can see, it makes this up and down less dynamic. The ideal case, you want it to be a straight line, and say under the area, under the curves of the same area, let me convert that into a straight line so that the area under the straight line is the same as before. Now that would be the ideal, but of course, in order to achieve that ideal, the reward has to be very high because you have to take away a lot of very time-sensitive traffic, and the objective function may say that A times the cost of exceeding capacity may not be so heavy that it means that you can send out any reward. That's also a cost term. So the balance between these two cost terms will determine how flattened you want to make this traffic profile look like. In other words, if I increase this constant A, the weight in front of cost exceeding capacity relative to the cost of sending our rewards, if I increase that A, then this will be flatter and flatter. So how can I describe how flat it is? One possible quantitative metric is that if I look at this straight line and then look at the difference between this line and one traffic curve, say the one before TDP, okay, in absolute value. So this will be counted just as this, and this will be counted. Okay, you add up those area differentials, we call that a residue spread. Okay, the spread between peak and valley. Then the residue spread should be a decreasing function of the capacity weight A. In fact, if I'm plotting a log scale here, and you see that indeed as A becomes heavier and heavier weight, ISP has more and more incentive to reduce the spread, and you see actually in this particular example at least a very sharp drop off, a cliff behavior. Now, what exactly should A be? That I don't know. There's no universally correct answer. It depends on the actual cost structure, again, which is very proprietary, sensitive commercial secrets of different carriers. But the general methodology is as we just described.